Hello, I'm Mr. McBrien. This is TEJ3M, Arduino 4, analog output from a digital device. Thought we'd start with a quote for the day. There are no eternal facts, as there are no absolute truths. Now, if you start throwing around Nietzsche quotes, you're probably going to run the risk of people thinking you might be cool. So I thought I'd give us another quote as well. So Obi-Wan would have said, "Only a Sith deals in absolutes." So what's that have to do with Arduino? Well, yesterday we talked about loops and variables. Today we're going to talk about pulse width modulation as well as applying our keyboard again. So first let's talk a little bit about analog versus digital. So digital implies ones and zeros, on or off, yes or no. Analog, sometimes we've taken it to mean old-fashioned, but analog can have any value, theoretically any possible value if you ignore quantum mechanics. Another way of looking at it is instead of on or off, it's on-ish, off-ish, and instead of yes, no, it's maybe. So what's all this have to do with the Arduino? Well, first off, let's discuss power gain for just a second. The definition of power, it's energy per unit time, or joules per second, or watts. And in circuits, we learned that power can be calculated as voltage times the current. Now, the output from an Arduino pin that is switched to on is 5 volts. I'd invite you to stop and think about what that tells us about the power output. So you can pause the movie for a second if you want to and see if you can work out what that tells us about the power. Return when you've given it some thought. Okay, so hopefully you looked at the equation above and said, I know my voltage is 5 volts. I know my potential is 5 volts, but I don't know my current. Well, we know that the potential combined with a given device tells us our current. So while we may not know our current, that potential will determine the current. Therefore, the potential in combination with a device tells us the power output. Now, that would be fine if we didn't care what level of output we got with a given device. If on was just on, if we dealt in absolutes. However, there are lots of applications where we want to be able to apply a specific amount of power and, perhaps more importantly, a situation-specific amount of power. So we might have dimmer switches where sometimes we want them to be low and sometimes we want them to be high. We might have motors where we don't always want to zoom everywhere at maximum speed. Temperature controls and other things. Now, we have a further complication that many of these devices don't support a linear response to potential. Combine that with the Arduino not producing a range of voltages and we've got a problem. How do we run a motor at 1/3 power? How do we light an LED at 1/3 of its maximum brightness? Now, if we return to our P equals IV equation, we can examine this and realize that if we drop the current, we drop the power. Now you can pause the movie again and think about how are you going to drop that current? How can we lower the current? Okay, coming back then, you may have decided that you're going to add a resistor to your circuit. Now there's a few problems with this. You're right, you're absolutely right. If we increase the resistance, we're going to decrease the current. But the problem is that resistor combined with current sends energy to heat. It would waste energy. It's also kind of hard to have an Arduino add a resistor in a situation specific time. Now, if our device behaved as a perfect resistor though, we could still use Ohm's law. We could change the voltage to modify the power. However, many devices don't follow Ohm's law. We already know one. The LED doesn't follow Ohm's law. In fact, motors don't as well. So we've got a real problem here. Now what's the solution? Instead of changing the voltage, instead of applying a resistor, we use a different trick. So if we want to get analog output from an Arduino, if we want our digital device to produce analog output, rather than changing the potential, rather than changing the resistance, what we're going to do is we're going to look at that time aspect. Remember, it's joules per second, right? So we're going to use the time aspect to vary our power output. And this is where something called pulse width modulation comes in. Instead of changing the potential from 100% to say 23%, what we do is we drop the voltage all the way down to 0. And we wait a period of time and bring it back up to the on state, bring it back up to 5 volts. But then what we do is we realize that if we switch back and forth, then the average power output is the average of how much time we spent at 5 volts versus how much time we spent at 0 volts. And then the only other trick we need is in PWM, we do the switching so fast that in the real world, whether it's a motor pushing our robot forward or an LED lighting, in the real world, the change is undetectable. So let's have a look at a few cartoons here. So what we can do is simulate given potentials by having the power at 5 volts for different intervals. So in the top case, we spend 75% of the time at 5 volts, 25% at 0 volts, and we get a 75% power output. The center case, 50-50, 50% output, and the lower case, 25-75 for a 25% power output. Now again, the switching back and forth is so quick that your eye cannot detect the fact that the LED is receiving power and then is receiving a potential and then 0 potential and back and forth. It's simply too fast for the eye to follow. So this kind of image showing us the duty cycle, how often the device is receiving power, shows us a simulation of voltages. So in the top case, it seems like our device is receiving 3.75 volts. In the middle case, it seems like 2.5 volts. And in the lower case, it seems like 1 volt. How do we achieve this? Well, in fact, the Arduino board has built-in PWM circuits on certain pins, and those are labeled for us. So this means that for those pins, we can use a new command. Instead of simply telling the system that the that the pin is high, we use the analogwrite command, specify the pin, and then give it a value between 0 and 255. So in the examples below, we have 128. That's approximately 50% power. You know what, we can call that exactly 50% power. And in the lower case, 25% power. So this command is going to be critical when it comes time to control the speed of motors and control the brightness of LEDs. And for this reason, we'll spend a bit of time developing some stuff now. So what I'd like you to do is write a quick sketch to use pulse width modulation to change the brightness of an LED at pin 9, for example, so you can use your sketches that you've used previously. Now don't forget your resistor, right? It's still getting 5 volts and you will burn out your LED if you don't have a resistor in your circuit. Now you can experiment with different brightness settings. I think you'll find some interesting results there. There are a fair number of PWM cycles on a red LED that will give you no visible light, for example. Now, if you find that really easy and you have some extra time, go ahead and set up a for loop to move the LED from bright to dim, back and forth repeatedly. It should be fairly pleasing to the eye. Okay, next, what I'd like you to do, if you haven't already developed the ability to pull from the serial monitor, go ahead and use keyboard input and pull an integer value and then translate that into your pulse width modulation intensity level. So if the user inputs a 0, turn the LED off. If the user inputs a 9, turn it to full intensity. And you may find that useful, that capability useful in future sketches, at least for debugging purposes. Now we're not going to go in depth into motors here because there's more to discuss than just pulse width modulation. We've got our first tool we need to work with motors. We're going to need a few more little tricks before we can work with motors safely. So we'll leave this for a future discussion. However, it is interesting to have a quick discussion about analog and digital now that we know how our system works. Remember that we have the numbers 0 to 255 to work with. Now, technically speaking, that is not analog. Why? Because we don't have the number 222.6375. You get the idea. We have a limited number of possible settings available to us. Now, analog is shown in the cartoon on the top. Our simulation of that is roughly what's shown below. Obviously, we have a few more values available to us than that output shows, but we still have that same kind of limitation where there are certain values that are not permitted. So technically speaking, the Arduino output isn't analog. There's a limited number of possibilities, but in general, that 256 potential values for us is sufficient for most applications. So this technical slide really is not important for our purposes. That analogwrite command for our purposes, for most applications, is an analog output. Okay, so let's wrap up then. Arduinos aren't designed to allow for analog output, but that's okay because many of the devices we use wouldn't accept analog output anyway. We can still control the power going to these devices. We can still get a maybe out of these devices, by using a built-in function in the Arduino for fast switching between on and off called Pulse Width Modulation. We do this using the analogwrite command, where we specify the pin and the value that we want to push out to it in terms of its duty cycle. For your homework then, please go ahead and complete those PWM sketches and feel free to go online to check out the references for pulse width modulation. Thanks very much and have a great night.